Dear students, let us see the next part of thermodynamics. In the last lecture, we have discussed what is thermodynamic system, what are the thermodynamic variables, types of thermodynamic variable, and types of system. In this lecture, we are going to learn about the thermodynamic equilibrium. Equilibrium means the name itself says that equality. Here, if the system is left to itself, the thermodynamic variables have tendency to acquire uniformity throughout the system. When complete uniformity is reached throughout the system, the condition becomes steady. The system is said to be in equilibrium. Means here system means what? Some kind of a fluid or gas that has kept in a container. We consider system like that. If a system is left to itself, the thermodynamic variables have tendency to acquire uniformity throughout the system. Means the thermodynamic variables means the temperature, pressure, volume, etc. If we do not disturb the system, the pressure of the system, volume of the system, temperature of the system, those remain same. That is what thermodynamic equilibrium. For the attainment of complete equilibrium, the following three conditions have to be satisfied. How this thermodynamic equilibrium can be achieved? By the two conditions. Those conditions, by three conditions, those three conditions are mechanical equilibrium, thermal equilibrium, chemical equilibrium. Mechanical equilibrium, there should be no unbalanced forces between the various parts of the system or between the system and its surrounding. There should be no unbalanced forces means there are some kind of force. In mechanics we have learnt about the force, torque, etc. And if a system that is kept somewhere, system means the part of the universe about which we are studying. That is what system. If there is no unbalanced force between system and surrounding, that condition is called as mechanical equilibrium. Unbalanced forces means the torque means the rotational force, the linear force, etc. of the molecules of the gas should remain same. That is what mechanical equilibrium. Next is thermal equilibrium. Thermal equilibrium means the temperature of every part of the system must be same as that of the surrounding. Temperature of every part of the system. If the system is divided into some 2 or 3 parts, then temperature of each part should be same. That is what thermal equilibrium. And the temperature of system and the surrounding also should be balanced. Next is chemical equilibrium. The chemical composition of the system should remain fixed and definite. There should be no chemical change and diffusion of matter inside the system. There should be no diffusion of the matter and there should be no chemical change between the system and the surrounding. Yesterday what we have discussed is the system that interact with the surrounding. System is diagrammatically we have represented the center part of through the circles. The center circle was the system and the surrounding we have represented with the larger circle and the system that interact with the surrounding. But equilibrium means specifically chemical equilibrium means the system should not interact with the surrounding. That is what chemical equilibrium. Thermal equilibrium, it can also be defined like this, means the macroscopic particles properties, means in the thermodynamics we learn about the macroscopic properties. Macroscopic properties means the pressure of the system, volume of the system, temperature, number of moles, mass, etc. These all we consider as a macroscopic properties, and all the macroscopic properties like pressure, volume, temperature, number of moles, mass, etc. of the system remains constant, then that condition is said as thermal equilibrium. Next, mechanical equilibrium, net force of the system or net torque of the system will be 0. That is what mechanical equilibrium means. There should be no unbalanced forces. All the net force and the net torque of the system should be 0. Means system means it should be a kind of a fluid or kind of a gas, like that. All the molecules should attain the same kind of a force and there should be same balanced force between the system and the surrounding. Consider a system means gas container that kept in a insulating material. Insulating means non-conducting and it is also called as adiabatic. A gas is filled in a insulating container or a adiabatic container. This is called as isolated system. there will be no transfer of heat, then the system is said to be in thermal equilibrium. As we have kept the gas molecules or the gas in the insulating container, as insulating means that will not allow the transfer of heat from the system to surrounding. As there is no transfer of heat, that system is called as isolated system. Because there is no transfer of heat, there is no change in the temperature, and pressure, volume, number of moles, mass, etc. remains the same. That system is called as isolated system, and the condition is called as thermal equilibrium. This system has attained the thermal equilibrium. That is what three equilibriums, and by these condition we can say that a system has gained or the system has attained the thermodynamic equilibrium. Next is zeroth law of thermodynamics. Now let us discuss an important law of thermodynamics, that is zeroth law. It states that if two systems A and B are separately in thermal equilibrium with a third system C, then the system A and B are in thermal equilibrium with each other. It states that if two systems A and B are separately in thermal equilibrium, let us consider three systems here, A, B and C. If two systems A and B are separately in thermal equilibrium with third system, means A is also in thermal equilibrium with C. Means there is a temperature of the system A is equal to temperature of the system C. And similarly, the system B is also in thermal equilibrium with the system C. Means temperature of the system B is equal to temperature of the system C. Then the zeroth law suggests that when two systems A and B are in thermal equilibrium, there must be a physical quantity that has the same value for both, and that physical quantity is what? Temperature. This thermodynamic variable whose value is equal for both two systems in thermal equilibrium is called temperature. Let TA, TB and TC be the temperature of three systems A, B and C respectively. If the system A and B are separately in equilibrium with C, then temperature of A is equals to temperature of C and temperature of B is equals to temperature of C. This implies that temperature of A is also is equals to temperature of B. That means the system A and B are also in thermal equilibrium. The significance of zeroth law of thermodynamics lies in the fact that two systems in thermal equilibrium must have a common characteristic called as temperature. Temperature is defined like this. The significance of zeroth law is that it has introduced a physical quantity called as temperature. To understand this clearly, this law, zeroth law of thermodynamics, let us consider three systems here, that is A, B, C. System is nothing but that has filled with some gas or some fluid. Let us consider that we have filled a gas in the three systems, system A, B and C. P is a pressure of the system, V is volume of the system, T is temperature of the system. As the boundary or wall between A and C is conducting, this marked or lined wall is non-conducting. That is what? Non-conducting or adiabatic. Non-conducting means there will not be the transfer of heat from a system to system. Means there is no change or the transfer of heat from the system because it is what? Non-conducting wall. Then, but this line, this is the wall or boundary between the system A and C, system B and C. But the wall between system A and B is non-conducting, but the wall between system A and C is conducting. Conducting means there will be transfer of heat from the system B to system C. As the boundary between A and C is conducting, there will be transfer of heat from A to C or from C to A. That depends upon the temperature of the system. Heat flows from higher temperature body to lower temperature body. So that as it is a conducting wall, there should be transfer of heat from A to C or from C to A. Then that depends upon the temperature of the body, that is the heat transfer from the higher temperature to lower temperature. Then both the system A and C achieve thermal equilibrium. Means as the temperature, if A have a higher temperature, the heat flows from higher temperature to lower temperature, then temperature of A will become equal to temperature of C. TA is equals to TC. As heat flows, temperature of both the system becomes equal, that is TA is equals to TB. Similarly, the two systems B and C will also achieve thermal equilibrium. Here B and C also achieve thermal equilibrium because here also the wall between the system C and B is also what it is conducting. So that heat also flow from B to C or from C to B. It also depends upon the higher temperature. If B have a higher temperature, heat flows from higher temperature to lower temperature. TB equals to TC. Because as heat flows, the temperature of both the system becomes equal, TB equal to TC. Later, let us remove this non-conducting wall and let us place a conducting wall here. Later, make the wall between A and B as a conducting. If we make the wall between the A and B as a conducting, and now let us observe here, is there any transfer of heat? But there is no change in the temperature of the system A and B. We have considered temperature of the system A as TA, B as TB and C as TC. And as the heat flow from A to C and B to C, temperature of TA is equals to TC and temperature of TB is equals to TC. As all the three systems have attained the same temperature now, so that as we have removed this non-conducting wall and we have kept a conducting wall here, heat has flowed from A to B. Thus we can say that system A and B are in thermal equilibrium because the temperature of A is also is equals to temperature of B. Therefore there is no transfer of heat. Hence from this experiment we clearly understood that zeroth law statement, that is, if two systems A and B are separately in thermal equilibrium with the third system C, then the system A and B are in thermal equilibrium with each other. That is what? A is in thermal equilibrium with C, B is in thermal equilibrium with C. That is TA is equals to TC, TB is equals to TC. Thermal equilibrium means the both systems should have same temperature. Here both systems should have same temperature. TA is equals to TC, TB is equals to TC, then clearly TA is equal to TB. That is what the zeroth law of thermodynamics says. So as we are discussing here about the factor temperature, thermal equilibrium means what should be remain same? Temperature should remain same. So the temperature, it is defined like this. Temperature of a system is defined as the property which determines whether or not a system is in thermal equilibrium with other system. Temperature of a system is defined as the property which determines whether or not a system is in thermal equilibrium with other system. Because to test whether the system is in thermal equilibrium, we are considering which factor? We are considering the factor temperature. So it is a property or it is a factor that determines whether the system is in thermal equilibrium or not. This is about the zeroth law of thermodynamics. Now let us define some more physical quantities here, that is heat, internal energy and work. We know that heat is a physical quantity. Now we need to define that. Temperature is a measure of hotness of a body. How can we define temperature? Temperature is also defined like this. It is a measure of hotness of a body. How hot the body is. That is what temperature. It determines the direction of flow of heat energy when two bodies are placed in contact. It determines the direction of flow of heat energy when two bodies are placed in contact. Means the heat flows from body at higher temperature to body at lower temperature. So that's why temperature is the direction of flow of heat energy. Now how can we define heat? Heat is a form of energy which flows from the body at higher temperature to body at lower temperature. It is a form of transfer of energy actually. Heat is a form of energy which flows from the body at higher temperature to body at lower temperature. The flow of heat energy stops when the temperature of two bodies become equal. That is what we have discussed in the zeroth law of thermodynamics, because heat was continuously flowing from the body at higher temperature to body at lower temperature until the temperature of both the system becomes equal, that is TA is equals to TC. That is what this point says. The flow of heat energy stops when the temperature of two bodies become equal. Then the two bodies are in thermal equilibrium. And what is the SI unit of heat? It is joule, and the common unit of heat is calorie. Every bulk system consists of large number of molecules. You know that a system means a system called as a system consisting of a gas molecules, or it may be a fluid, and it contains large number of molecules. Then this second factor called as internal energy is defined like this. Internal energy of a system is sum of potential energy and kinetic energy of all the molecules in the system, and it is denoted by U. We know that the molecules, they may be continuously flowing. Gas molecules means they continuously flowing, they continuously collide each other, so that the internal energy is sum of the two energies, that is potential energy of each molecule plus kinetic energy of the each molecule togetherly, that is called as internal energy of the system. The internal energy is one of the parameter which represents the thermodynamic state of the system. So internal energy is also a thermodynamic variable. It represents the thermodynamic state of the system. Then sign convention of internal energy. Increase in internal energy, it is taken as positive. Decrease in internal energy is taken as negative. If we increase the internal energy, then that energy is positive. If we decrease the internal energy, the sign convention is negative. When heat flows into the system, its internal energy increases, because when we heat a body, all the molecules gets energy, then they start to collide. As they start to collide, their kinetic energy increases. Similarly, the internal energy is also going to increase. When heat flows out of the system, its internal energy decreases. As the body or a system loses the heat, its energy decreases. Heat is one mode of changing internal energy of a thermodynamic system. Heat is one mode of changing the internal energy of thermodynamic system, because when we heat a body, internal energy decreases. When heat flows out of the body or out of the system, internal energy decreases. So it is a one mode of changing the internal energy. Then what is the other mode of changing internal energy? It is work. The other mode of changing internal energy of the thermodynamic system is work. By doing work also, we can change the internal energy of the system. So work is defined like this. Work is said to be done if a body or a system moves through a certain distance in the direction of applied force. Work is said to be done if a body or a system moves through a certain distance in the direction of applied force. We have already discussed this. Work is what? Product of force and the displacement. As we apply some force, the body moves, and that is what? Work done. Consider a cylinder fitted with a frictionless piston of area of cross section A. Let a gas be contained in the cylinder. The wall of the cylinder are perfectly conducting, so that gas in the cylinder is in the thermal equilibrium at temperature T with its surrounding. This cylinder is completely filled by the gas, and there is a piston. It is continuously moving. Area of this piston is A. So that it is what? If we are moving this piston, we are doing some work here. So that here the pressure, volume, temperature of this gas molecule is going to change. If we compress the gas, there will be change in the pressure, volume, temperature. If we expand the gas by dragging this piston, there will be again change in the pressure, volume, temperature. So that the internal energy is going to change. That is what? Work. By doing work also, we will change the internal energy of the thermodynamic system. Let P be the pressure of the gas on the cylinder. Then the force exerted by gas on the piston of the cylinder is given by force is equals to pressure into area. Pressure is force per unit area, so that force is equals to pressure into area. Let piston moves through a small distance dx during the expansion of the gas. Therefore, the work done by the gas is given by, work done is what? Force into displacement, and force is, we have defined like this, force is product of pressure and the area. So substitute the value of force here, that is force is pressure into area into dx. In this diagram, if we expand the gas, means as the piston moves upward, it has moved some distance dx, so that work done is force into displacement. By applying some force, we have moved the piston, so that expansion of gas has taken place. That is what the work done, dw is equals to force into displacement, and the force we have defined as pressure into area. Substitute here pressure into area into dx. And what is a into dx? A into dx is dv, change or increase in the volume. How can we define the volume? Volume is length into breadth into height. Here height is what? Dx. This much height gas has expanded, so height is dx here, and a is there, h is dx. Length into breadth into height is the volume. Length into breadth is nothing but area. Area is equals to what? Length into breadth. So in the place of length into breadth we have area, and in the place of height we have height dx. So that a into dx, can we say that is volume? Yes, it is volume, that is change in the volume. Then work done dw is equals to p into a into dx is what? Dv. dw work done is equals to pressure p into a into dx, we got the value as dv. Work done is equals to p into dv. If volume of the gas increases from initial volume Vi to final volume Vf, then the total work done by the system or gas can be calculated by integrating equation 1. It is what? Small work done. Small work done through the distance dx. But initially the volume was Vi. Now we have expanded the gas, so that with the help of piston, so that volume has changed to Vf. Here value is Vf. Here value is Vi. Now by integrating this equation 1, we'll get the total work done, that is integration of dw, small work done, from Vi to Vf is, value of dw is what? P into dv. In the place of dw, substitute here p into dv, where p is a pressure, that is constant pressure of that gas. P, integration of Vi to Vf dv. P is constant, it is outside. Then upper limit minus lower limit dv, integration of dv is V. Then Vi to Vf, integration of dv is V. In the place of V, substitute Vf, upper limit minus lower limit Vi. It is what? Expansion. If the system is compressed, in the first case we have expanded it above with the help of piston. We have expanded the gas. If we compress the gas, means if the piston has moved downward, if we compress the gas, its volume decreases. Hence work done on the system or gas to change its volume to dv during the compression is given by work done dw is equals to here minus p into dv, because volume is going to decrease when we compress the gas with the help of piston. That is work done dw is equals to minus p into dv. Here negative sign indicates that the volume dv decreases. Hence, total work done to decrease the volume from Vi initial value to Vf final is given by total work done dw is equals to minus Vi to Vf p into dv, where this p, that is pressure, is constant. Similarly again the upper limit Vf minus lower limit Vi. Integration of dv is V. Substitute the value of V, that is Vf minus Vi. Volume is changing from what? Changing from initial value Vi to final value Vf. That is Vi to Vf minus P, Vf minus Vi. Then the total work done W is equals to P Vi. Here minus is there. We can change the limits here by taking minus outside so that it become positive. P Vi minus Vf. Sign convention for work done is work done by the system is taken as positive. Work done on the system is taken as negative. If the system do the work, that is positive. If we do the work on the system, then that is negative. That is what work.